I had a person in one of my classes this, without getting into the details, there's HIPAA rules that prevent me, test positive for COVID-19. And then Friday, I started getting a cold, and this weekend I had a cold. So I went in Sunday, and strangely enough, a few other people, one other person I know in our department who's a faculty had similar symptoms. So I went in to get tested at one of these urgent care type places on Sunday, and they said I didn't have COVID, but it was a rapid test. So then yesterday I went to see my doctor. This was a regularly scheduled appointment for like a 6-month year physical type of thing. And he suggested I get tested for the antibodies. So I got tested for the antibodies, and now I'm waiting for them to get back to me to see if I had COVID, because he said if you had it, even if you have it, still have it, you'll have the antibodies. So I'm waiting on that. He hasn't got back to me, and that's why we're doing Zoom. Just an explanation. I think it's in order. And I'll try to be as transparent and clear about anything that has to do with this virus for everybody's sake. Now, I want to tell you this. If you have the virus, you don't have to tell me. But if you want to, I'll do everything I can to help you. And if you need me to bring you, literally, if you need me to drop off a quiz or something, or just drop off some information, I will. And because this is a time like none other, if there's anything I can personally do, and probably other people in this class, to help you, let us know, including get groceries for you, anything like this. One thing we're trying to do is, in any way, shape, or form, if we can help people survive this crazy time, we will. So that's my spiel on this one today. And now, first thing I wanted to do is take any questions you had about the homework. I had one email question about calculating mu and epsilon, mu relative and epsilon relative for a problem I gave you. I'm not sure who asked me that, but I hope I answered the question sufficiently. Is the person on here that asked me that or not?
Yes, sir. You answered it. I got it now. Yeah.
And that was, I'm not sure if it was 611 or what problem it was.
612.
612. Does anybody else have other problems about the homework? Anything else? No. Usually I get at least one or two, but this is a Zoom meeting. Have I had anybody for a Zoom class in here or not? What did I have you for, Ashley? Oh, Carlin?
For signals?
Oh, God. I'm so sorry. That was a rough, sorry. I think I'll be a little better this time. Any questions? Okay. All right. Well, so just to go ahead and just sort of, I guess, bring everybody up to speed in a review. We're talking about propagating electromagnetic waves. You don't have to write this down, but you know we started with the Maxwell's equations, the curl equations. We developed what's called a wave equation from that. And then we talk about propagating waves at a great distance. Do you all follow me on that, guys? That's where we were, right? Then we found out a few things. One was, in general, the electric and magnetic field in the far field were given. Here, I'm going to write this down, and let me know if for whatever reason it's not clear. I hope you see this. In general, if we talk about a source of propagation, I'm going to say it's propagating in the z direction, but the electric field is polarized in the x direction. So the propagation is like this. It's propagating this way. The phasor rendering of E for this would be really E vector phasor. It's just a vector on the top and a phasor. In your book, the E will be bold, and that will not be a tilde over it in Whitworth's notation. But I just want to tell you, the way you always tell a phasor is looking for the J quantum. This is rendered as some magnitude, call it E0, e to the minus gamma z in the AX direction. This is the standard notation Dr. Whitworth is using in his book for a wave propagating in the z direction oriented in the x direction. The corresponding H field would be equal to some, actually H vector phase are equal to some, just H0. It would have the same type of form, e to the minus gamma z ay. And it would also be divided, well, really, I'm just going to leave it like this. These are the two forms. Now there's a relationship between the magnitude of E and H.
Dr.
Excuse-
Baginski?
Oh, the focus, I'm sorry. Is that what you're going to say?
Yes, sir.
I'm sorry about that. I got to turn off this autofocus. What? All right, guys, if the focus for whatever reason is poor, let me know. I've turned it to manual, but I don't know how this is going. Anyway, these are the general things. Now, the first thing I wanted to mention is the relationship between the magnitude of E and the magnitude of H for a propagating wave. This is only for propagation, is eta, and that's the intrinsic impedance. And eta is given in general as the square root of j omega mu over the quantity sigma plus j omega epsilon. And that means if you have a propagating electromagnetic wave, and I stress this, this is for a propagating launched wave, that when you take the ratio of the propagating electric field, assuming only one component, if you take Ex over, in this case, Hy, that will be equal to eta. Now, how many remember that, right? From last time, going over it? And I gave you problems with this, didn't I, that had this thing embedded in them, correct, class? Right? Not much, but a few. So that's generally true. The way you always get it if you're talking about propagating waves, and these are the two things that are golden, and it's on the bottom of page 327, are given by the cross product equations. Now, what I'm going to do, this is the bottom page 327 in your book. I'm going to rewrite these, and I want to talk about something and ask you a question, if you don't mind. So if we have these two equations for propagating waves, in general, if you wanted the H field and you had the E field and it was propagating, it would be equal to 1 over eta. That eta value can be complex. And then it's a unit vector. A sub p is just has a magnitude of 1. It's in the direction of propagation, crossed into the E field. Now, I should actually put a phasor there, but I'm really not going to. It's when you see something where you have, this will work in the time domain, but in general, the way E and H is designated tells you exactly if it's phase or time domain. And there's a second rule, and that is that if you have H and you want E, it would be equal to minus eta, and that's the intrinsic impedance. Then it's a unit vector in the direction of propagation crossed into the H field. Now, those two things are golden. You should know them. I'm going to do an example. Last time, I don't believe I did an example of this. Did our class? No. So give me 1 second. So if I want to ask everybody to do this with me. Suppose I have this, and we talked about a electric field that was propagating not in X, Y, or Z, but in two components. Do you remember that? Where we talked about how to get the vector direction propagation? Do y'all remember that class?
Yes, sir.
Okay. If I want to just say that you can do this for any type of direction of propagation. I'm going to keep it simple for this one, just so we're all on the same page. If I give you this as a quiz, this is quiz 1, so to speak. I'm going to say the E field, E field is given as 2 e to the plus j, and I'm going to put 10 Z AX. Can everybody see that okay? The default units for the E field are always volts per meter. I don't put that down because it's an assumed fact unless I state otherwise. Is everybody okay with this? Okay, now if that's the E field, and we assume we're in air, all right? And I ask you, typical quiz question, what's the H field? And I'm asking this for free space with the information given. All right, what are we gonna do with this? Anybody? It says free space, I'm not done yet. Anybody?
So do you know that the direction of propagation is the negative z direction?
Yeah, how did you know that though? You're absolutely right. What did you look at?
In the exponent of the e, it's j10z, and for it to be in the positive z direction, it would have to be minus j10z, and then if it was in the y direction, it would be minus j10y or something.
Does everybody hear him, class? Can you all hear him talk? Could you hear Jack or not? You did?
Yes, we could hear.
Just let me know. If you can hear him, he's absolutely right. So one thing we can say is a unit vector in the direction of propagation would be equal to minus AZ. Does everybody understand that? Right? Okay, next, not you, Jack, somebody else. Next, what is the intrinsic impedance if it's in free space? This is anybody except Jack. If you answered, please don't answer again.
120 pi.
120 pi ohms are about 377. Does everybody hear that? Okay, you with me, everybody? All right, so that's 120 pi ohms. We're getting there. So now when we look at this, if we wanted H, we've got eta, we've got the direction of propagation. Now we have to do the cross product. Do you all agree with that? With me? All right, so now I'm going to say H is equal to 1 over eta. I'm going to go ahead and put 120 pi. You don't have to. Then it's the vector direction of propagation, which is minus AZ, right? It's crossed into the E field, right? Well, the E field is in the AX direction, so it's 2 e to the j times 10z AX. Does everybody see what I'm doing? And why I'm doing it, more important. Correct, class? It's kind of funny. I see, and I really appreciate you turning on your cameras. It helps me a lot, but I only see a couple of people, but that's okay. First of all, I mean, some way of indication. You see, if I see, if you nod, it's easy. I know it's hitting that thumb sometimes takes you away from your writing. Everybody follow me on this part, right? All right. Now, what happens here? When we get AZ, forget the negative. AZ crossed AX is what? Think about X, Y, Z, X, all positive, right? So Z crossed X is positive AY, isn't it, class? Correct, class? But when the negative sign's here, it would be minus AY, right? If we have Z, X, AY, but it would be minus AY. Do you all see what I'm doing, class? Are you all follow me on this? I've got AZ crossed AX. That would be plus AY, but there's a minus, so it'd be minus AY. So the H field here would be equal to 2 over 120 pi. Then it would be e to the j times 10z, right? And it would be minus AY. Do you all follow me? Okay, we're not done yet. Now, if we have that, that's the exact answer, but typically we would actually reduce that. We'd take 2 in the 120 and make 60 pi on the bottom. I'm just showing you typically what you do. And then if you've got a calculator, you would make it fractional. You take 1 over 60 pi if you care to. And the units of H are amps per meter. And that would be correct. Now I'm going to show you one other thing that you're going to find very, very valuable. just as a rule of thumb to check yourself. And I think I mentioned this last time, but I'm not absolutely certain. There's a cardinal rule in electromagnetics for propagating waves, is if the right-hand rule will always dictate whether you're right or wrong about the vector directions. If you take, and I'm going to put it right here, E crossed into H, that's actually the vector direction of propagation, but it's one other thing. It's also the power, average power flow. Now, I'm not going to spend much time on this right now, but it always gives you the vector direction of propagation. So if I take E crossed H, I'll always get the vector direction of propagation. Use your right hand. Everybody's got a right hand. Take your index finger in your right hand. This is how you do a cross product using whatever they call handiness. Take the index finger of your right hand and point it in the direction of the E field. Well, you see the E field in this case is going in the AX direction, right? So I'm going to assume AX is up because it's consistent with Wentworth's book. Then take it and you have to make your thumb like an axis or an axial line. Don't move that. And you have to cross that or move this in through the shortest angle, 90-degree angle, into the vector direction, the Y direction. Well, it's minus AY, right? So minus AY, if you think about it, if X is up, X crossed, I'm trying to do this. If you take X, I'll do it here. If this is X, right? X crossed, this would be Y, and this would be Z. I'm showing you a right-hand coordinate system, right? So X crossed minus Y would be crossing this way. So if you take your finger and go this way, you see it's pointing in the minus Z direction, don't you, everybody? Can you all see that, class? Just take your right hand, try it. Yeah, and that's the proper direction of propagation. So we have the H field with a minus sign here. That's minus Y. In fact, it agrees with the handiness rule. Did I show you that thing? E crossed H equals direction of propagation last time, right? That's generally true and it works, always works. So a couple other things I want to do with this example. Somebody else? Now I've got this information. Here's another thing I could do. Here's kind of the quiz right here. So if this is my quiz problem, I got that. I want to know the velocity, phase velocity, which happens to be the group velocity or the velocity of energy because it's an unbounded wave. How would I get that if I wanted the velocity, anybody? Or do you have enough information to do that? All right, let me ask you this. It's an air. What does that tell you right away? If it's an air, what's the velocity of propagation? Anybody? Anybody at all?
Is it the speed of light?
Sure, it is. So that was kind of a trick question. Isn't it right? It's the speed of light, correct, class? And what is the speed of light about?
3 times.
You're right. 3 times 10, sorry for cutting you off, 8 meters per second. Actually, it's what? 1 over the square root of mu naught over epsilon naught. Correct, class? Right. So we've got the velocity of propagation. Now, keep working with me here. What's the wavelength? These are things I typically ask on a quiz just to make sure everybody understands the basics. So how would you get wavelength, somebody?
Isn't it the speed of light over frequency?
Yes, for free space it is. You're absolutely right. Technically, the fundamental definition is what? It would be omega over beta. That would be the fundamental. That's usually what people go for, right? Isn't that right, class? Oh, I'm sorry. Sorry, this is speed of light. I'm putting this here. So I'm sorry. You're absolutely right, lady. This is speed of light here. But if you have lambda, it would be phase velocity. Actually, lambda, let me show you something about lambda, and I'm going to do it right here. I want to make sure I'm clear about this. You're absolutely right. C over F is correct. when we talk about beta, think about this, beta right there times lambda. This would be the argument of the cosine. And I think I mentioned this last time. This has to be equal to 2 pi. Let me explain why again. The product, beta is inside the argument of the cosine, right? It's beta z. Well, if beta z is equal to 2 pi, that's exactly one wavelength difference from the argument when it was 0, right? And it's back, the phase goes back to the same point in the cosine argument. So beta lambda is always 2 pi, and therefore lambda is 2 pi over beta. Now you have beta right here, don't you? It's 10, class. You all see that? So if beta is 10, I can get wavelength as 2 pi over 10. Now watch. That's in, Lydia, I think you said this. That's C over F, right? But what's the problem here? Can you see a problem? Do we have F, class? Well, yes and no. I didn't give you F, did I? But what do we know? We know this is true, isn't it? You all with me on that? 2 pi over lambda, or 2 pi over beta is lambda. Do you agree with me there at least, right? If that's lambda, so don't you have the frequency necessarily if you have lambda? I got ahead of myself, but right? And you even said it, Lydia. You said if you have lambda, which is 2 pi over 10, that is C over F, right? So it's 3 times 10 to the 8th over F, so you can get F. Do you agree with me? This is the point I'm going to make. Anything that's traveling in air, any electromagnetic wave traveling in air or in a vacuum, you know is traveling at the speed of light. And because of that, if you have beta, you have F. And by the same token, if you have F, you have beta. The two are inseparable. Follow me? Got it? So this is the kind of problem I give. And here's where you people fall short. They will remember this formula of phase velocity is omega over beta, but it will not strike them that you're in air, therefore you know the speed of light, so you know, and you know beta because I gave it to you, so you can get omega, things like that. There's an, you might say, they decouple the formulas, like they don't assume one necessarily links to the other, but beta and lambda are inseparable. E and H are inseparable. If you have one, you have the other, if you know the environment. Wavelength and frequency are inseparable. If you have one, you have the other. And I'm trying to make that case. Now, for this thing, there's one other thing I can do is get the power density. And I think I was talking about that last time, wasn't I? Right at the very end of the lecture, I believe, class. So first of all, are there any questions about what I did here at all? This is sort of just going over the basics, isn't it, class? Really just the basics we've covered. Any questions? Okay. So let me go ahead, turn the page. And now, if you're looking in the book where we are, I'm going to be talking, you don't have to turn in there, but if you got your books, it helps. This propagation and lossless charge-free media we'll talk about, but that's free space, really. Well, it's not always free space. It could be something, it could be like polystyrene or something. But in general, you look at free space and modify the velocity. Here, when it talks about propagation and dielectrics and it gives these equations, don't pay attention to those. You got great calculators and calculate those. You don't need approximations. I mean, these are exact, but your calculators will get these just by using the general expression for gamma. Remember, gamma is alpha plus J beta, right? So in general, I tell you, just use that to get beta and alpha. You don't need to mess with that. It's nice if you're trying to be elegant and stuff. We'll talk about low loss dielectrics, and we'll talk next about propagation in conductors. But before we do, I like jumping ahead and doing the Poynting vector. So if you're following along, I'm going to jump to problem 6.5, or section 6.5 and then come back. And what I want to tell you is this, that when we talk about the electric field's power density as it propagates, this is the real critical point. We've done E and H. We found out how they're inseparable if it's propagating. We also found out that both frequency and wavelength were and beta were all coupled together. They're inseparable. If you have one, usually you have the others, assuming you know the medium. So now the next thing we're going to do is find power density. And if you have an electromagnetic wave propagating like this, if it's an electric field and it's propagating, necessarily it has an H field that's associated with it. And it also has a power density. It's an average power density that's flowing in the direction of propagation. Now, the way we talk about power density and the way Dr. Wentworth's book is going to talk about is this. We're going to talk about average power density the same way you talk about power, or I say average power when you're dealing with your power courses with Dr. Gross. P-Av itself is equal to, and this is in his book on page 184, it's 1/2 the real part of E cross H conjugated. This is on page 344. If you want to take a look at your book, it's equation 6.84. I want to mention something. This is a vector. And I want to do this one time. It's no need for you to write it down, but it's nice to see it at least once. I'm going to use Wentworth's notation. So in general, we have an E field given as some E naught, E to the minus, and here it's going to be alpha Z, I'll assume it's propagating in the Z direction the way he does, times E to the minus J to beta Z, AX. All right. We're going to have a value of intrinsic impedance eta, which is some magnitude of eta at a phase angle, E to the J, and this would be the phase angle of eta. Now, the reason I did this is because, remember, eta can be complex, and the formula for eta, the general formula, is square root of J omega mu over sigma plus J omega epsilon. So it can be complex. If it's lossless, this phase angle is 0. It'll just be strict real, okay? Now, if I have this, I can get the H field. I can say the H field is 1 over eta, unit vector in the direction of propagation, crossed into the E field. In this case, from this waveform, a unit vector in the direction of propagation is AZ. And I think everybody understands why, right? If you look up here in the argument, beta's coefficient is Z, and there's a minus sign, so it's in the positive Z direction. Correct, class? Everybody follow me? All right. Now we have that. Eta here is going to have a magnitude and a phase angle, so just watch. We're going to have this in AZ, that is AX, would be in the positive AY direction. When you have AZ crossed, AX would be positive AY. And here we can see that H in general would be equal to 1 over the magnitude of eta, right? Has the phase angle E to the J theta eta here. Then it would be the magnitude of the E field, which I'm calling E naught here. Sorry, that's E naught. It would be E to the minus alpha Z, E to the minus J beta Z. And I'm going to do one other thing. First, everybody take a look at this. Y'all follow me that this is just E naught here. Eta is now a magnitude, but I take the phase angle and I break it out in terms of the superscript of the exponential. Are you all with me here? class? All right, now what I'm going to do is this. Well, what happens if I have 1 over like e to the j 20 degrees? What is that equivalent to? Isn't it just e to the minus j 20 degrees, class? With me? If you take an angle from the denominator to the numerator, the angle is just negated, isn't it, class? Y'all with me on that? Got to make sure everybody sees the subtleties. So what I'm going to do is get rid of this and make this e to the minus j phase angle associated with eta, okay? Everybody good with that? All right, then the next thing I'm going to do is this. I'm going to go ahead, I'm going to execute this, but I want to do one thing. I'm going to ask everybody what happens here. What is H conjugated going to be? That's H, isn't it? Right? Remember, it's general, right? E is anything, eta is anything in terms of its magnitude. But when I conjugate a vector, what happens? Well, if I had like 10 at an angle of 20 degrees equal to A, what would A conjugated be? Anyone? Are you familiar with the term conjugate? How many?
And at negative 20 degrees.
Sure. It just takes the angle. If it's positive, it makes it negative. So it'd be 10 at an angle of minus 20 degrees. All right, one last thing. What if I had B equals to 2 plus J2, not you, Jack, somebody else, and I want B conjugated? What would it be? Anyone?
2 minus J2?
Yeah, the only thing you're going to do, the real part stays the same, and you're going to put a negative sign in front of the J. And you flip the sign in the J term if it's got if it's really done in what they call rectangular coordinates, where you have a real and imaginary parts separate. Correct, class? Now, when I go ahead and I conjugate H, what happens? Well, E naught and magnitude of eta are scalar. They stay the same, right? Now, e to the minus alpha z, that's a strict real number. There's no imaginary term in there, so that stays the same. Now, when I conjugate, I take any negative j, and what do I do with it? Or I flip the signs in the j's, don't I, class? Change the angle, correct? So this becomes what? E to the plus j beta z, e to the plus j theta n. Take a moment and appreciate this. The only thing I did is conjugate H, correct, class? Now I'm going to go ahead and take the E field I have here, the H field I have here, and I'm going to plug it in this equation. I'm going to execute that. So here, it's not really a big deal, but when I go ahead and do it, it's going to be equal to, and I'll do it right here. Now I get the average power flow. That's a vector, would be equal to 1/2 the real part of the E field. I'm rewriting this. That's crossed, and I'm going to circle that cross product, crossed with the H field right here. It's going to be E naught again over the magnitude of eta times e to the minus alpha z. Then it's e to the j beta z, and then e to the j theta eta. I hope you can all see that. And again, what I've done is nothing more than sticking into the upper equation that I've taken off the chart right there. This equation, the E and H I solve for. Follow me on this, guys. And let me increase the magnification a little here while I talk about this. Okay. Now take a look at this. Look inside this argument first. You see how I have E naught and E naught here? right? That's E naught squared. I'm going to take this down here. P av would be 1/2, right? The real part of, that's the E naught, and E naught is E naught squared divided by eta. So put down E naught squared over eta here. These are all strict real, right? What happens to this term? E to the minus alpha z times E to the minus alpha z. What does that become? Anyone? E to the minus 2 alpha z, correct? Right? Can you all hear me okay? Right? Isn't that just E to the minus 2 alpha z? Right? And then I have, this is the important part, E to the minus j beta z times E to the plus j beta z. What is that? Well, think about this. If I have E, right, to the j5 times E to the minus j5, isn't that E to the 0? Class, yeah, add the exponent. What is E to the 0 in your own words?
1.
1. So what I can do is just get rid of that. That's my point. Now I'm finally left, these are all real. I'm left with this last part, which E to the j theta n. And what is AX? I didn't put it down here, but this is, I wish I would have. This is actually in the, H is in the AY direction, right? Sorry, I didn't put it down here.
Wouldn't it be negative AY?
No, remember, H is going to be, this is AZ cross the E field is AX, ZX is Y, right? Positive AY? Isn't that right? Who asked that question?
I did. I was doing it with my hands, but it came out to be negative. Maybe I did it wrong.
Well, if you think about it, if you just look at this equation right here, can you see it?
Yes.
All right, that's AZ crossed into AX would be AY, right? The way you do this, if you're a little rusty on it, it's X, Y, Z, and back this way is all plus, right? And then when you go this way,
I can't see what you're doing.
okay, I'm sorry. It's, if you go X crossed Y cross Z back to Z, this is plus. This is the way I think you taught that in one of your math courses. And but if you go the opposite direction, Z, Y, or back to Z, it's all minus, right? Like X cross Y is plus AZ, Y cross AY cross AZ is plus AX, and so forth. You follow me?
Okay, yeah.
Did you all get this? Did you see this or not? I think you get it in your vector courses in linear algebra or calculus. One of them, you get them in one of your courses. I just don't remember which ones. All right. So now when I have X crossed Y, it would be AZ out here. Correct, class? That's my real point. Now, follow me on this. I'm taking a long time, but there's some points I have to make. You see how this is strict positive? I mean, there's no imaginary component, right? But when I look at the real part of this, well, if I have E to the j theta, that's cosine of theta plus j sine of theta, isn't it? According to Euler's? How many know that? It's Euler's identity. You kind of have to know that. So if that's Euler's identity, the real part would just be cosine, wouldn't it, class? Right? Y'all remember that real part? So this whole thing will boil down to this, and this is true for propagating waves always. Propagating waves in the far field will have the form of average. This is assuming it's a plane wave in the far field. Will be P average will be equal to 1/2 magnitude of the E field. It's really E naught squared over magnitude of eta times E to the minus 2 alpha Z here times the cosine right here of the actual angle associated with the intrinsic impedance. And remember, theta n, theta sub n, eta, right there is really the angle of eta. Are you with me? Now we're going to get down to some interesting things. This is real important. So that's just power flow in general, but we're going to use this equation. It's power flow of a plane wave. We're going to use this equation to do a whole bunch of interesting things and beneficial things. And so now we're going to look at some regions. I'm not going the way Dr. Wentworth's book does. I'm going to look first at the actual power flow in a good conductor. So put down good conductor. So when I say good conductor, that probably rings bells of copper or a metal, right? Gold. A good conductor is something that doesn't resist current flow. Copper wires, gold, silver, aluminum, these are very good conductors. But here's how you tell a good conductor. And let me be frank about this. You look at the curl of H equation. When I was doing my doctoral work, my major professor liked to turn this thing to Maxwell current density. He would call this J sub M. There's a lot of people I had were physicists that taught me. What this is the total current density, displacement current, as well as real current flow. And this, remember the curl of H was equal to J, right? Plus the partial of D with respect to T. J is real current. It's electrons or some other charge carriers that are moving. They're actually moving a long distance. The partial of D with respect to T has to do with bound charge at best. And really, it's just something that has to do with the electronic or the electrical repulsion or attraction of charges on the plates of capacitors. That's where I like to explain it and think about it. Now, when I take this and put it in a phasor form, the curl of H becomes J, right, plus J omega D. And then when I go ahead and replace J and D with epsilon E for D and sigma E for J, I get this. I get sigma E plus J omega epsilon E, right? That would be curl of H. Agreed, class? When you have a good conductor, it means this is much greater than this. So for a good conductor, what we have is this. Sigma is much greater than omega epsilon. You see how the E's would cancel if you literally did the ratioing? E would appear here and here, right? So it's really, if sigma is much greater than omega epsilon, then you have a good conductor. And a good fundamental question to ask is, well, how much is much greater? I don't know if you've ever thought about these things when you're told. In a sense, there is no scientific way to say that, but the simple way is if sigma is 10 times omega epsilon, this is the general rule of thumb I've always been using and been taught, then it's a good conductor. It's a fantastic conductor if this is 100 times. If sigma is 100 times omega epsilon. So one thing you'll notice, it depends on the frequency a great deal, whether you're dealing with a conductor or a dielectric, doesn't it? Because omega right there, if omega is 0 or DC, then anything's a good conductor. Do you follow me on this, class? And really what we're talking about, time varying phenomena, but this is the general rule. So if we have a good conductor, and that's true, keep looking at this now. Please be attentive here. First thing you notice is eta is equal to the square root of J omega mu over sigma. Sigma is much greater than, that means this is about equal to the square root of J omega mu over sigma, doesn't it? All with me on this? This is an important point. Now, if that's the case, take a look what happens. Well, I got the square root of J there, don't I? Well, and this is a little discussion I like having. J is equal to what? Isn't that e to the J pi over 2 radians? Isn't that really what J is? How many know that? All right, sure. If you look in the, if this is the real axis and this is imaginary, the vector e at 0 is here, and e to the j pi over 2 would be right there. It would have a vector length of 1. It would be at 90 degrees to the real axis. So this is the same thing, right? Y'all with me on this? So what happens if I have the square root of j? Well, that's the square root of e to the j pi over 2, correct? And what is that? If I have e to the anything, and I take the square root of it, it's really e to the anything divided by 2, isn't it? So this is really e to the j pi over 4, correct, class? With me? I'm really not trying to bore you. I'm just trying to be clear. So if that's the case, well, what is e to the j pi over 4? Isn't that the cosine of pi over 4 plus j sine of pi over 4? Right? Using Euler's, correct, class? And what is the cosine of pi over 4? That's the cosine of 40 degrees, which 45 degrees, which is it's 1 over square root of 2, isn't it? Yeah. So this is 1 over the square root of 2. And sine of 45 is 1 over square root of 2. So it's 1 plus j times 1 over the square root of 2 is this. And the reason I'm saying that is if you look here, you have j, but you have a square root operator. So what I'm going to do is say eta right here is really equal. And if you take a look at this with me, as really the square root of omega mu over sigma. That's just these. And it's really times e to the j pi over 4 or 45 degrees. And the only thing I've done here is taken my definition here and replaced j with e to the j pi over 2 and then taken the square root operator and pulled that out. Y'all follow me on this? And what that means is this is a scalar quantity, but it also means that this is equal to square root of omega mu over sigma. And then you're going to be e to the j, you could call it 45 degrees. Isn't that right? Right? E to the j pi over 2 is what? I mean, pi over 4 is 45 degrees, isn't it, class? I'm doing it for a reason. Now take a look at this. Here's where it gets important. We know if we know the E field, getting out of time. If I know the E field in a good conductor, and here I'm going to just call it E naught, e to the minus alpha z, I'm going to assume that the E field's in the x direction, times e to the minus j beta z in the ax direction. Then I know that the H field associated with this would be E naught over eta. Well, eta will have this value right here, magnitude of eta, but there's an e to the j 45 degrees right next to it. And I can take that upstairs as e to the minus j 45 degrees, and I'm doing it for a reason. And then it would be e to the minus alpha z times e to the minus j beta z, and it would be in the AY direction. I'm about out of time, so bear with me. So what I'm trying to show you is E and H will no longer be in phase. This is the first thing. Can you all see that? Everybody follows me. If it's a good conductor, E and H are out of phase by 45 degrees. See that right there, what I've circled? Now, the next thing I'm going to show you, and this is real important. If you don't, does anybody have a class right after this one? Anybody at all? Let me know. Anybody? All right, how about, I'm going to call this the office. I'm going to finish this thought. It's real important that I try to get this out here continually. And I'm not going to go long. If you have to go, you have to go, but bear with me. Next thing I'm going to tell you is, what is gamma? It's the square root of j omega mu times sigma plus j omega epsilon, isn't it? Right? And that's alpha plus j beta, isn't it, class? Now, this is, again, for a good conductor. What happens here? Well, if it's a good conductor, look in here, what happens? We assume sigma is much greater than omega epsilon, right? We can get rid of that. And now we've called it approximate. If we get rid of this, what do you notice? Gamma for a good conductor is equal to the square root of j omega mu times sigma, correct? And you got that square root of j then. So what do you notice happening? Square root of j, I can put down as e to the j pi over 4, or I can render it as 1 plus j. This is how it'll be in Dr. Wentworth's book, times divided by the square root of 2. That's the square root of j. And I did it right here. Right? I took e to the j pi over 4 and I made it this. I hope you can see this. I'm trying to keep this all on one sheet. So the square root of j is that, and then it's times the square root of omega mu sigma, right? You guys with me still? I'm almost done. Now look, what is omega in terms of f? It's 1 plus j here. This is going to be, I'm just rewriting this first part. 1 plus j over the square root of 2, but watch what I do. I have the square root here. Omega is 2 pi f, right? Sorry. Omega is 2 pi f times mu sigma. And I had the square root of 2 out front. I'm going to pull it inside, so it's 2 here. And that means this is 1 plus j times square root of pi f mu sigma. And since gamma is equal to alpha plus j beta, you'll notice that alpha, the coefficient of 1 and the coefficient of j are identical. And what this means is alpha equals beta equals the square root of pi f mu sigma. For a good conductor, I hope you can see it right there. Can everybody see that okay? You want to know where it is in the book? You probably do. If you look at this is on page 335, equation 6.58. And the real point I wanted to tell you, and I don't have time to elaborate, is that the phase velocity, when you take a look at the phase velocity, this is still a good conductor, is equal to omega over beta. Well, when you do that, I'll just tell you, that's omega over the square root of pi f mu sigma. And that's in Dr. Wentworth's book on its equation 6.63. But here I just, what Wentworth does in his book is he puts this as 2 pi f and he reduces it. I like to do it this way. So that's the phase velocity. My point is, one last point here, is that this velocity can be many, many, many orders of magnitude less than the speed of light. All right, as a matter of fact, if you carefully choose the value of frequency and sigma, you can actually get velocities of the order of 10 or 15 meters per second. And I'll speak more about that next time, but that's the direction of propagation. Okay, did you understand today's lecture, by the way? Okay.
You mind going back to that last page real quick just for a second?
Yeah. And by the way, why don't we call this an office hour? If you need to go, go. But if you want to stay and ask questions or have comments, please do so. I'm trying my best here to help everybody. And if I miss something, let me know how I can improve it. Sure. William, is this what you were asking about?
Yeah, that's perfect. Thank you.
Carlin, did you have a question or was that wrong? No? Okay. And Tyler or Lydia or yeah. You can go ahead and speak.
I'm good. I was just staying to listen.
Okay. Well, I wanted to do an example of some of this stuff, but you got to understand if I what happened here. All right, I got to tell you something. Sometimes I see what's happening. Everybody's dropping out, so this thing automatically adjusted the size. I can put you, can you all see yourself or not? Right in that page or not?
No. It's just
Okay.
your screen.
I can see you, though. That helps. All right. So did you have any further question, William?
That was it.
All right, what I wanted to do is this. This is the real thing. I didn't get to skin depth yet. Have you heard the term skin depth? We'll talk about this next time. There's something called skin depth. And what it is how far down a wave effectively travels in a material if it's conducting. And when you look at the propagation, remember, I had the E field, just bear with me. The E field was equal to some E naught, right? E to the minus alpha Z, then it's E to the minus J beta Z, right? And here, I'm gonna just tell you, I'm propagating in the Z direction for a reason, AX. Now, if you look at this just for a second, this waveform really is some magnitude in phase, and it's decaying as E to the minus alpha Z, isn't it? Just look at this for a second. Do you agree with that? You see, this dictates the magnitude of everything, right? If I have alpha Z equals 0, then the magnitude is just E naught. The phase term does nothing for the magnitude. But if alpha Z is, say, 1, that's E to the minus 1, or 1 over E. Now it's decayed to 33% its value, roughly. If I have E to the minus 2, it's decayed to maybe 2 or 1 or 2%. And what they do is arbitrarily say that the skin depth is something. This is the skin depth definition. I wish I had time to get to it. Is equal to the point where the magnitude of the waveform decreases to E to the minus 1, its peak value. And let me give you an example, because that doesn't mean much. What you do is take this component and say E to the minus alpha times skin depth, and the symbol for skin depth is that, is equal to E to the minus 1. And therefore, the skin depth is simply 1 over alpha. So the skin depth for a material is 1 over the square root of pi f mu sigma. And this is for a good conductor. Did you have this anywhere, guys? William or Carlin or Lydia or Seiko? Do you remember the term skin depth from anything? No? Well, I want to tell you this. When you're dealing with electromagnetic phenomena, if you try to propagate into salt water, it doesn't go anywhere. It just shorts out. Most of it's reflected. Did you ever see the movie? It's called Red October. It's a movie about a submarine. Anybody? No. Well, submarine communication forbids the use of electromagnetic energy at high frequencies when the sub is deep. The only way they can communicate is either using a sonic or sonar signal or with an extremely low frequency. And the reason is this. Remember, the skin depth is a figure of merit of how far down the wave goes. You see how that frequency there is 1 over the square root of f? Well, if you're at 10 to the 10th hertz, which is 10 gigahertz, or even 10 to the 6th hertz, 1 over the square root of those things is extremely small, especially for seawater, because sigma is fairly good in seawater. And that's why skin depth prohibits the propagation of waves through deep into the sea and also in conducting earth. Now, there's a lot to be said about this that I'm going to speak next time, but that is skin depth. I'll put it on my notes and I'll give you homework, okay? Did you have any further questions about the homework I assigned? Anybody? Go ahead,
What's the
Lydia.
first variable under the square root?
Let me write it real clear and show you where it is in the book. The skin depth is equal to 1 over the square root of pi
Okay.
times f times mu times sigma. In your book,
Page 341.
and 337 actually is the best, because Wentworth does what I just showed you there on page 331 right there. Can you see it? E to the minus 1. Oh, I hate that reflection. E to the minus 1 is E to the minus alpha times gamma. Oh, and therefore, delta, and therefore delta, or the skin depth, is 1 over alpha is equal to this. Can you all see it? By the way, does everybody here have a book available to them? Carlin, Seiko, Lydia, and William? Okay. Now, any other questions about the homework that I assigned? I'm going to assign some more questions, but I wanted to cover conductors first. Then a lot of this stuff makes a lot more sense that Dr. Wentworth talks about. You all with me on that? So when we're talking about propagation and good conductors, you're really talking about propagation in the earth generally, or in seawater, or in metal. And some people will say, why even talk about it? Well, it's real important to talk about it for practical reasons when you deal with phenomenology of ground penetrating radar or really some shallow type of imaging, but I'll get to that later. Are there any other questions before I break it off? And I appreciate you staying up with me. And if you guys need an office hour after you take a look at this stuff, let me know. Can you do that, guys? Just send me an email. If you need an office hour and need to answer questions, and I'll try my best to do so. This lecture okay with you guys? You understand it okay? Now we're going to do Fridays this way. And I'm only doing this because I'm still waiting on my test results, but I think I have to quarantine this week. Did anybody else have any exposure or hear about anybody with COVID or anything like that? No? William, you okay with that? Would you do me a favor, William? You're going to put this stuff on YouTube and put it on the GroupMe link, right?
Yes, yes.
Could you make sure you send it to me and I'll send it to the whole class, or post it on the OneNote, please? Okay.
Okay, yeah, perfect.
All right,
I'll-
guys. You take care. Thank you.